substations are filled with transformers. Lightning strikes and transformers are destroyed. But utilities all know, I'll just pull a number out of the air, maybe 6 companies have one truck already loaded with a new replacement transformer. So all they have to do is get a tractor and move that transformer to their station and put it in. I don't know, did any of you knew about New York City being out of power for an hour and a half? Or for a day and a half? It happened. Maybe 30 years, no, it's been probably 40 years ago now. 2 plants in New York City area had lightning strike in their switchgear room outside the substation. And that took two nuclear plants out of service. And at that time, those plants were not licensed to restart without federal government approval. So my boss and I were on a phone for 2 hours, not together, but every 10 minutes we talked. There was no yes or no or good morning or goodbye or anything. He'd give me the questions that Washington wanted to know, and I'd give him the answer that I got from the previous question. So for 2 hours, we got those 2 plants, the world, the utility and the federal government, got those 2 plants back in service, and were generating enough electricity to supply their own pumps. Everything in the plant was supplied with power from their own internal power generated by nuclear power. And to make a long story short, 2 more events occurred. First of all was Indian Point losing two plants. The second one was a big thunderstorm that existed for a long time in New York City. A coal plant, the biggest they had in New York City, was struck by lightning. So it got taken out of service, and they were dragging power then from Canada so strong that these wires, you've seen these substation wire, or the big power transmission lines, the wires were so heated that they were sagging, and they were shorted out intermittently with touching trees. And then the third event, 2 hours later, was that they were dragging power across the Hudson River into New York City from Maryland, Pennsylvania, and New Jersey. And they were dragging so much power that they overloaded the breaker. So now all power for New York City was out of service. By this time, Indian Point's back in service, could have been in service, but not synced to the line yet. So by the time the third event occurs, there was no place to put power. So New York City was out of power for a day and a half. Again, it shows what can happen if the federal government and the utilities are working, using all their resources to get back in service. That just didn't happen quick enough. Questions? Okay. I already said that mechanical equipment, electrical equipment, all is subject to failure. And so plants are built to be able to test plants and make sure that whatever failures occur, the failed components are found and removed and replaced. And I already said that fuel elements recently in service have to be cooled, forced cooling. Now, radioactive material is always emitting, and I'll give you an example, is radiation is nothing more than an energy bullet that goes wherever it goes. It can go anywhere, and you've all seen pool tables. So those silver bullets reflect off of air, off of something else, and every time it hits something, it loses energy. And so that's what happens with radiation. It finally either goes way out of your range, or it's bounced around so much that it's ineffective by the time it hits you. radiation goes by two means. In the case of Japan, they lost a lot of radioactive material to the outside world, including the ocean. You probably read that a lot of fission products did get in the ocean, and the ocean is huge. But again, the coast of California is being inundated with radioactive material transmitted by water and diffused between Japan and the United States. But radioactive material is now on the West Coast. You probably never heard of Chinese fallout, Chinese bomb testing fallout. I was in Fort Worth at the time, and of course we had an underground bunker which is where our control system was, and it's pretty well monitored with radiation detectors. And we were taught that whenever alarms go off, get outside, only to find out that the radiation that we're monitoring is coming from Chinese bomb fallout. And so Chinese fission products are falling on grass. Cows are eating the grass. Cows are giving milk with radioactive material in it. The media never told you that, I don't think. But I know what my radiation dose from Chinese bomb fallout was because I monitored it all the time. But again, it's fairly low level, and media didn't report it, and your body is not affected by Chinese bomb fallout unless you had it. If you're alive, some of you are too young to have lived at that time, but the radiation is everywhere. I already talked about containing fission products. One thing I want to tell you about fission products and fuel outlets is there are, in the United States, we do not reprocess fuel, and we should. As the fuel is pulled out of a reactor, more than 50% of the U-235, which is fissionable material, is still in and usable in removed fuel elements. We should be reprocessing those fuel elements and recovering all of that very valuable material. Instead, you think fission products are bad stuff. They have to be put in a cask, and they are, and they're stored. About a month ago, there were articles in the Kankakee paper about stored fission products in all nuclear plants.
Can you talk a little bit about the politics behind that? With that?
But
With Yucca Mountain, not in Nevada.
Yeah. So, politics, dirty. You know who Harry Reid is? The chief in the Senate, and you know where he's from? Nevada. He's a senator from Nevada. He personally is very anti-nuclear, and he does not want fission products stored way underground in his Nevada. So as politics go, when Bush was president, Harry Reid was able to hold up all approvals of all Bush appointees for a long period of time until his man got appointed as the commissioner, one of 5 in the NRC, the Regulatory Commission, which is where I work. And so finally, to get somebody appointed, Bush did appoint this man to be a commissioner. And then when the new president was appointed, he made that anti-nuclear commissioner the chairman of the 5. And he was chairman at the time the Japanese event occurred. And so he had published a memo saying that all further study of the nuclear burial site in Nevada will cease. The Supreme Court has now overruled him, and the Supreme continued again. I think it will happen. I don't know how much more politics is going to be involved, but the value of a burial site is that the fission products that exist, some of them have a half-life, and I'm going to tell you what that is in a minute, but a half-life that is thousands of years long. And a half-life means that whatever the level is now, and I'll use the number 100, if it takes 14 days is a half-life, that means in 14 days, the 100 is now 50. So that's the meaning of half-life. And the half-life of plutonium is thousands of years, which it is. That means it doesn't put out a lot of fission products per day, but it does mean it puts out fission or radiation for a long, long period of time. So the key to fission product storage is to take those long half-life materials and put them in a burial ground, which is the vat. Questions? Yes.
So when you were talking about that senator that you said doesn't want any like fission deep into the ground, so is there none in Nevada then, or is that like a federal thing? Is it state by state, or is it federal?
Well, that's probably where it will be, because it's deep in the ground. And what they're studying is when earthquakes occur, do they occur at a level as deep as what that site will be? So, and again, what happens with earthquakes, usually you end up with a bunch of rubble around, and if it inundates that plant, nobody can ever get there. Who cares? So, will it be approved? It's been a long time, a whole career for me, that it has not happened yet. But will it happen someday? I think so. And the other thing that I think is very disgusting is that the United States Nuclear Navy right now reprocess fuel. And they reprocess it in Nevada, or in Idaho. I was at the Idaho station. I saw the plant that reprocesses fuel for the Navy. And so the good U-235 that comes out of used fuel elements goes right back in. The unused part goes right back into new fuel elements. Additional U-235 is added, and you got new fuel. Concept when I first got in the nuclear power business was that there would be a nuclear power plant site with 8 big reactors and 1 reprocessing plant. And you've ever heard of breeder reactors? Okay, when fission occurs, there is 2.5 neutrons that come out for fission. There is no such thing as a half a neutron. So it's the statistical number, meaning that of fission, some of them are 2 neutrons come out, and some of them are 3. So the average statistically is 2.5. And for fission to occur continuously, you have to retain 1 of those 2.5 to go into the next generation to cause fission. And reactor shutdown always has a neutron being shot into the pile of fuel, always. And so whenever you pull out a control rod, the fission rate, 2.5 neutrons, most of them are eaten up by absorbing material. And when you finally get to the point where you inject 1 neutron, you get 1 retained for continuous power. If you want to raise the power, you pull up the control rod, and now I get 1.1 retained neutron. And the 0.1 is giving me a higher fission rate in the second generation. So that's the way you increase power in the reactor. One other thing I ought to tell you is that fission is a nuclear bomb. Fission is a reactor producer, is heat producer. The difference is, in the case of a bomb, you want the fissionable material to be so compact that the 2.5 neutrons that are born, instantly, each 2.5 goes into another generation. So you want generation after generation, very rapidly. And when you do, you have a bomb. In the case of a reactor, you want the increase in the power level to be at a very, very slow control rate. And the difference is that bombs have high concentration of highly fissionable material. A reactor never has high fissionable material. It's only 7% as compared to 92.5 in the case of bomb material. So there's two things that keep a reactor from ever being a bomb. One is that the concentration of fissionable material is not large in a reactor, and the fission material in a bomb is very, very concentrated. In the case of a plutonium bomb, they want it so concentrated that they have a sponge. Plutonium is in fact a sponge. So around that sponge, there are detonation, little explosive materials to compact that sponge into one very compact bomb. So a bomb is fission, a reactor is fission. But a reactor can never be a bomb, and a bomb is highly concentrated and very explosive. Questions? Okay, meltdown. Almost all accidents, media picks it up as a meltdown. And meltdown has various meanings. I told you already that zirconium melts, and it does. But that does not say that the fuel pellet within the fuel rod melts at the same time. In fact, the fuel melt temperature is more like 4,000 degrees Fahrenheit as compared to zirconium is about 2,000. So when they talk about melting of reactor core, be careful. What was the temperature at the time it happened? And was the zirconium that melted, was it a lot of it, or was it just a very, very small amount? Many reactors have had some melting of zirconium, but never has it been in the United States that had any major consequence. Questions? Accidents. I already talked about Chernobyl being the big baddie, and the crew was assigned to do jobs that never should have been assigned. They were not trained to do it safely, and as a result, and Chernobyl had no containment. In other words, the big shell that's around all U.S. reactors, they didn't even have it. So when they got the rupture of high radiation levels, it was all released to the atmosphere. Widespread radiation on soil all around the plant. Also, they had big, heavy fires, so there were killing of people in the case of Chernobyl. The United States at that time did send representatives from the United States over to Chernobyl. One, to decide, do we know something that can help them to rescue people or rescue soil or rescue equipment? And it turned out that a fellow that used to work for me was one of 5 that was over there as part of that team. And also he was over there, they were over there to determine what should we do financially to help those people. In the case of Japanese, I already told you that we had a chairman who was very anti-nuclear. So to my knowledge, there was no U.S. support for the Japanese. One other comparison between 3 Mile and Japan. I already told you that I got the call, and within 15 minutes, your federal government was fully involved in trying to recover that plant. What I did was, one, we had an emergency center already established in our office. Two, we had also performed drills so that I knew it was going to be at night, but I didn't know when and I didn't know what. But I knew they were going to have a drill in our office. Twice we did that. I happened to be assigned in Washington for a while. At the time, Washington had a drill. And on a drill, you pull out all your emergency procedures, you pull out all the plant designs and drawings and operating procedures. So you're in full contact with what the plant people should know. So that you got knowledgeable people talking to knowledgeable people in all offices. I think you all know that the more people who know what they're talking about talk, they all come to a conclusion that this is what we ought to do. And so, the United States, when 3 Mile was involved, the right people were in the right place talking to each other. We also did not have any inspectors in 3 Mile at that time. So, when the radiation dose was as high as it was, we already had 2 cars already at the office, sirens and lights. So we put knowledgeable inspectors in cars with police escorts and sent them over to 3 Mile. Meeting. It took about an hour and a half for them to get there, but as soon as they got there, they were measuring radiation levels all around the plant, people in the control room at the plant to help and examine what maintenance people were doing. In the case of Japan, it's now 3 years later. And if newspapers are correct, and I don't say they are because I don't think they are, but they're just now getting Japanese federal government involved with recovery and repair of nuclear plants in Japan. So gross failures in Japan by all counts. And again, another thing that Japan did not have, they did have some safety equipment that said that U.S. plants have 3 cooling systems that back up. Apparently, and this is newspaper again, reports that they did have safety equipment that could have been put in service, but their own plant operators didn't know where they were or how to use them. So, again, training is very, very poor for those crews. Advantages of 3 Mile Island. Our office was very involved with recovery and correction in 3 Mile. And so our government, our office, and all inspectors had what we call bulletins. And so all plants that needed to make changes in plants were getting bulletins at rapid rate, that this is what needs to be corrected with training, with your operating procedures, with your equipment, the way you do things. Our office was issuing as many as 3 bulletins per day to change things and make them get fixed. Big changes, 2 things. One, you all know what a simulator is, do you not? So all U.S. nuclear plants now have a simulator. And they typically needed 3 crews to rotate shifts and take care of vacations and things like that. Now plants have 4 crews. So they got 3 for operating and 1 for training on the simulator. In a simulator, you can postulate all kinds of nasty things that could happen. Have you ever been in a control room in a nuclear plant? Well, you take that wall and this wall and load it with recorders and instruments and red lights and green lights and all that. What does it mean if you got 2 red lights there and 1 there and 4 over here? What does it mean? And hopefully they're trained, hopefully they got good judgment, but what chance do you have of every time guessing right? Now with a simulator, All of these things are postulated, so that when an operator sees those things, one, there's a computer back there that says this pump stopped, or this valve didn't close, or whatever. But also, they've been trained so that automatically they know they've been through in the simulator exactly what you. Day one, in that I think you know that the first reactor was at Chicago Stands, and then it blossomed into the Eisenhower days when they wanted universities to have reactors. So there were a lot of reactors around. And so in the meantime, I was first in an aircraft company in Fort Worth, Convair at that time, and found out that they had night courses at SMU in nuclear power. So I took night courses, and then I come to find out the company had a nuclear program, which is a test program of reactors that supplied radiation to destroy whatever parts might become radioactive, or because of radioactivity, oil wouldn't work and wouldn't lubricate anymore. But before they built airplanes to be nuclear powered, they had to know that some things worked and some things didn't, because radiation damage is a problem, or can be a problem with equipment, particularly with lubricating oil. And so then things happened. So finally I went to the East Coast for new big reactors, power reactors. Any of you familiar with Dresden, or where it's located? Or Braidwood? Big 1,000 megawatt reactors. And so that's when I got really in the big business of big reactors. And so it's been an interesting career. And my problem now is that because of 3 Mile Island, I think the general public has become very anti-nuclear. And so during this time period, I'd like for you to understand that nuclear power can be very reliable and very safe, in spite of the fact that two biggies, Chernobyl in Europe, and more recently, Japan. How many of you are familiar with recent catastrophe in Japan? Good, good. Because I think that's a perfect example of what not to do, and they got in big trouble. And how many of you are generally familiar with 3 Mile Island? Okay. And I was the first one with the federal government that got the first phone call on 3 Mile Island. And 3 Mile Island should not have happened, but it did. And the thing to remember on all equipment, whether it's a car, whether it's a filling station being filled with gas, cars being filled in filling station with gasoline, things can happen. The equipment breaks down. 3 Mile Island had a valve that opened inadvertently. And when you open a small valve in a pressure system that's 4,000 pound pressure, you lose a lot of water in a big, big hurry. And the one thing to remember on nuclear power is never, ever let a reactor shut down, but not have cooling water over the fuel elements. And for 8 minutes, 3 Mile Island did have no cooling available. And the problem with not having cooling available is a reactor is providing heat for steam for electric power to generate electricity. And an operated reactor, 100% of the power is fission, is 90%, and decay of fission products is 10%. So you can shut off the fission entirely, immediately, and that's what does happen. But the thing to remember is that 10% of the power that was generated is still generated by decay of fission products. So you have to have cooling. And if you don't, then the zirconium which is a can. Fission products are within a reactor and a fuel rod. The fuel rod is about that big around. Little pellets inside a zirconium tube, and it must be sealed and stay sealed. And if it melts, then the fission products are released. And that's what happened in 3 Mile. 4 o'clock in the morning, and here you have a reactor. And you have the reactor vessel itself with pumps. Let's see. No, the reactor's over here. And what you have is cooling water, what's called the primary system. And then you have the heat being transferred from the first loop to a second loop over here. This is radioactive water. This is not radioactive water coming over to a steam generator. And that's the way electricity is generated. So it's pretty simple, straightforward engineering tactics, things that you know all about. You've all had water sprinklers watering the lawn, and you convert potential energy, which is the pressure in the tube in the hose, into kinetic energy, which is the water that's sprayed out of the hose. And that's all a steam generator is. Making a fan go to generate electricity, which is what's up here. So engineering principles are all pretty normal. And it's not something that's tough to learn. It's there, and every engineer is trained to know how to handle it. So when nuclear power is being built, one has to know these engineering principles. Nuclear power plants are built much more rigorously than any other business except space. All metal is subject to what we call blowholes. You've all had loaves of bread. You cut them open and there's a big bubble where there's no bread at all. And metal that's poured like steel is exactly the same. You can have holes in metal as it's poured. Nuclear plants are all guaranteed to never have blowhole any place because you want strength. Nuclear power is very, very new. We don't know, or didn't know when they were first built, what radiation would do to steel. So what all nuclear plants is, they have a little coupon that's in the reactor itself for one reason: to irradiate it and find out what the metal properties are over time as a direct result of radiation on the steel. What we're finding is that steel is not affected very much. So the licensing time of a nuclear reactor is being extended from 30 years to 60 years because the steel is intact for the first 30 years. So things are changing, we're finding out. I talked about critical things in the construction of a reactor. All wells are radiographed. That means they're taking an X-ray of every piece of every well, every reactor piece of the pressure vessel, which is over here, is like 6 to 8 inches of steel. And you're going to have 4,000 pound pressure inside that vessel. The reason you have that much pressure is that you want all the water that goes across the fuel elements, which is represented right in here. You never want a bubble. I think you've ever all seen a pan of water on the stove, and bubbles collect on the bottom. And whenever bubbles collect, you lose good heat transfer. So in a reactor, the zirconium, at all times, you want it to be water, never steam bubbles. Never steam bubbles, because you want good transfer. You want no spot to be hot in that zirconium, because if it does, it could be so hot it melts. And if it melts, you have a metal water reaction. metal-water reaction creates hydrogen. So now you have another potential problem in that you got hydrogen in the bubbles that go through the reactor itself. And so that's going to rattle a pump, and you're going to lose some bearings. So you do not want hydrogen within the water. But even worse, if the hydrogen gets out of the pressure vessel, which is this vessel right here, and gets out into containment, which is out here, there you have air. And whenever hydrogen mixes with air, you can have an explosion. Those of you that talked about the Japanese people, they did have hydrogen explosions, which take the top off of the pressure vessel. 3 Mile Island had zirconium melt. It did create hydrogen, and hydrogen did get out of the pressure vessel into containment, the big shell around it. How many of you have ever seen a nuclear plant? Big building, and it's big heat exchangers where the steam comes out, excess steam comes out. So you do not want any fission products to get out of the containment. There we are. You see those big buildings? And these are the cooling towers where the excess heat is drained to the atmosphere. In the case of Redwood, they have a big cooling lake in the strip mine ponds, so they just circulate cooling water around, that is heated water from the plant around in a big circle, and that's the way they don't heat the excess heat. So, questions? Anybody have a question on anything I've said so far that you didn't understand? Yes. Oh, okay, you just hold it up your hand. Okay. Now, if you have questions, please stop me and ask, because I hope you understand that reactors can be safe. In the United States, they are. It turns out that 3 Mile Island did lose a plant, but in no case was the radiation levels outside the pressure vessel itself or outside containment. Never was it high enough to cause any physical damage to anybody in the company, or never was it as high outside the plant as it is in the halls of Congress every day of the week. So that's a pretty profound statement, but it's true. When I got the call initially, they gave me a radiation level that I'd never heard of before. So I instantly knew we had a big event. And when I'm talking about radiation level, it's inside that big containment vessel where the radiation fission products were in there and very high level. But never did fission products get outside that big containment vessel, in spite of the fact that there was a hydrogen explosion within containment the afternoon of the first day. So, yes, they had potential, had problems, but never did human beings have any injury, even in the plant or outside containment. Don't remember how old, you couldn't have been very old when that occurred, because it was 30 years ago now, but it's kind of hard to believe. And the problem with the event at 3 Mile Island was that the movie issued 2 weeks before the event at 3 Mile Island. And what the movie projected was that the heat generated in the pressure vessel was so high that the fuel melted. To my knowledge, never did there have fuel melting, but we did have zirconium melting. And with the fuel melting, it melted through the 6 inches of steel at the bottom and down through containment into the ground. And in the movie it said went all the way to China, through the world. Not likely, probably never will happen. even in the worst of case. Chernobyl did not melt fuel that much, and the Japanese, they say, did have melting through the pressure vessel at the bottom into containment. To my knowledge, it did not go into the ground. So, radiation reactors create a lot of heat, and I hope you realize that a lot of heat has to be handled correctly, or you can have big problems. Questions? Afraid? Yes.
I think in the Japanese situation, it did go into the groundwater, and that's why they're erecting that, the ice wall to help it not go out into the sea.
Yeah, I don't understand what I read in the newspaper, because one thing indicates that the water from the hill is picking up radiation that came out and is on the ground, and that's where the source of water is, or radiation is. But I've also heard that it's leaking from the plants, so I'm not sure what the source is. But stop and think again, how in the world do you have a dam of ice in the ground that's going to be there for 10 years? So it doesn't sound very practical, but I don't know the first-hand situation either. But in the case of the Japanese now, they did blow off the top of the containment. So fission products got out. The reason the Japanese situation is so bad, they had 6 reactors at one site. And when in my outline, when I talk about locating a reactor correctly, they removed 30 meters of soil. So they get it down to solid rock, which is sea level. And when the SICE came along, which was the big water waves that came from the sea, why the total reactor site, all 6 reactors were flooded. If they'd left that soil in place and put in steel pier or concrete piers to be anchored on concrete, why they'd have been above, the plants would have been above the water level. So location of plants is very important. Another thing with U.S. reactors is that I think you know that all equipment is subject to failure. All equipment I know of is subject to failure. Reactors are built to operate for 18 months with no shutdowns of plant. So control systems are built so that you can lose 1 sensor out of 4. And you better not lose more than 2. And what's required by license conditions is that when 1 fails, you detect that failure somewhere in the next short period of time by testing all 4. And if 1 has failed, replace it. So now they've got an intact control system again. But first of all, it's built to stand the failure of 1 sensor. And by license conditions, they have to test all 4 periodically. And if one of those 4 is failed, then you have to replace it. Questions? Nobody asleep yet?
Can you take us through the difference between Chernobyl and 3 Mile?
Yeah, Chernobyl. I don't know. That was really a catastrophe they asked for. You know what interlocks mean? If I want nobody to get out of this room, I put an automatic lock on the door. And until I push the button, you can't get out. But in Chernobyl, they bypassed interlocks. And so, sure enough, they were doing experiments that never should have been planned. Never in the world should they have planned the experiments that they did. So here we are, doing things that you ought never to do with the reactor. They asked for big trouble, they got big trouble. Radiation, go back again. We had a case surveyed in our office in the Philadelphia area where a man was in charge of radiating fuel, or radiating food, I mean. And what he did was piled up food that wanted to be radiated to purify it, so there are no germs in the food at all. Had interlocks on the door, that once he pumped it up, then the locks on the door were all locked, where he could never get into that room. Well, again, he goofed. He bypassed the interlocks. And operating foodstuff, the horribly huge source. And then he went out and realized that I better go back in and do something. So with the interlocks bypassed, he walked into a very high radiation area. So high that there was first 50% probability that he killed himself. And our office got called. We had lots of people on retainer and could call university professor and have him take charge of medication for that person. And what happened with him was that the white blood count in his blood was all that was being made in the bone marrow was killed. And so what existed in his bloodstream was deteriorating over time. And for 17 days, his blood count was going down and down and down. And he got such a high dose that there was a 50% probability he would die from the radiation. So the blood count goes down and down for, and I think it was 17 days, but it was something like that, I know. And it went down and down and down. And finally on the 17th day, as that's the right number, it was at its bottom. Then the bone marrow started reproducing, had been reproducing over time, but it got to the point where now the bone marrow is feeding good blood cells back into his blood system. 2 days later, he was discharged from the hospital. Well, so the body is quite capable of repairing itself, but be careful. So radiation standards allowable for people is set at a number which is well below anything that's going to be really a problem to you. Unknown to you, probably, did you know that radiation is everywhere? The chair you're sitting in and the room you're in right now is radioactive. And radioactive with what we call background radiation. And you're sitting in an airplane on the ground, you have one radiation level, which is pretty low. You fly up at 30,000 feet, and it's much, much higher, just because there's a lot of air between 30,000 feet and the ground, and that 30 feet is destroying some of the radiation that's in the air. So do you understand background radiation? It is everywhere, including your own body. You two are sitting close together. You're each irradiating the other one right now. Background radiation. But the body itself recovers cells on a periodic schedule, something like 7 years. So every cell, I shouldn't say every cell, but most of the cells in your body are replaced automatically. God made it that way. So the cells that are destroyed in your body by radiation will be replaced and are. So that the radiation tolerance level is set to the point where the cells that are destroyed by allowable radiation are replaced before the body has any problem. No problem with radiation concept. I personally have been in the business since 1955. I'm 90 years old. I have been in pretty high radiation areas, such that you have to have double suits of clothing to protect yourself from particulate matter, and I'm monitored. And again, the key to safe entrance in radiation areas that high is don't stay very long and don't stay very close to the higher radiation levels. So time and radiation and a radiation level makes all the difference in the world. As long as you're protected, clothing-wise, as long as you don't stay in high radiation very long, you are healthy. As far as I know, have no health problems. None. Age 90. Questions? Yes?
What kinds of clothing did they make you wear when you went into those high
Just
radiation?
common ordinary coveralls. And you wear booties on your shoe and you wear protected head also. And many times you're in gaseous problem areas and you carry gas mask. So, do you understand radiation and how you protect yourself from radiation? You understand background radiation. It exists all over and it's measurable.
You guys listen closely with your tick. That's coming from the Geiger counter that's located on the desk. It's just picking up radiation in the background. So, Mr. Bruner said.
So newspapers like to pick up the word radiation and scare the bejeebers out of people. And that's fair game, but you, the listener, be sure you understand that they know what they're talking about. Are they talking about high radiation or long duration in high radiation? Or is it low, that the body can totally tolerate those low radiation levels? Question? In your outline, I wanted to talk about reactor designs. And I already talked about the Japanese having located those 6 reactors on rock at sea level, knowing it's earthquake-prone country. So a big mistake of location. Another thing, U.S. reactors are all built for earthquake. So that if an earthquake would occur, and they talk about long-term radiation levels in this area. You've never heard of an earthquake here ever. But our plants are built to stand earthquake. And when I say built to stand it, I'm talking about pipes. And pipes are all over the plant, carrying steam or water throughout the plant. An earthquake is a vibration phenomenon. And so what is the frequency of the earthquake? They're all different. So if you've got a long section of pipe, I think you've all stretched a rubber band and then blow on it, sure enough it vibrates. And you pull it tighter and it vibrates at a different frequency. You pull it tighter and it vibrates at a different frequency. So the designers of nuclear plants, again, have to worry about what frequency is the earthquake if it occurs. And what they do is they have what they call snubbers. So as soon as the earthquake is detected, 1, the reactor shut down. 2, snubbers go in and grab every piece of pipe. They're there only for earthquake conditions. And if the vibration that they're built for is exactly right, then that's everything within the containment, the big shell, everything is just one solid chunk. So that if the big building is upset, you got everything rigid inside that containment. So they're protected from earthquake. They're also protected from, I'm talking about containment now. It's protected from airplanes flying into them just like they did into the World Towers. Heavy load of gasoline or fuel and big bang. There's some heavy impact of an airplane against a building. So they're protected against that. And they're also protected against terrorist attacks. So that Have we protected everything? Wouldn't guarantee it, but we sure tried. Questions? How's the time?
Doing good.
Okay. I said before that the heat generated in a reactor while it's operating, 10% of the heat that's generated is fission products, decay of radioactive material within the core. And you want to be very, very sure that there's always forced pumping of water around all of the fuel elements within the pressure vessel. And to make sure, when the reactor is shut down, automatically one piping system is cut off. Don't know whether it's pumped, don't know whether it's a broken pipe, don't know what it is, but replaced with a separate piping system and a separate supply of water. And in most plants, there's 2 backup systems. The first one doesn't give you cooling water, the second one better. And then you've still got convection cooling. You know what convection cooling is? If you had something in a pan of boiling water, the water tends to rise as it heats, and that's what you call convection movement. So when they finally, if the other 2 systems fail to cool that core, then you do get convection cooling. So backup systems are very, very important. And again, nuclear plants are built with separate power supplies so that electricity shuts off your incoming power. You have diesel generators that start. In the case of the Japanese, they realized that they goofed when they built those plants at sea level. So they built 3 big diesel generators high and behind the plant and wired it in. And when the plants themselves got flooded, killed all the diesel generators' power, they had them wired in, but by this time all the pumps and motors are flooded, so they can't operate. Utilities in the United States all have spare parts, and some of them are big transformers. You've all seen substations.